Hello students, welcome back. Now let's go to section 3 and discuss the computational aspects of prime numbers. First, let's discuss how to find prime numbers. Given candidate, it's easy to find out whether it's a prime or not, at least theoretically. All we have to do is to divide by all the integers between 1 and that number and find out all possible factors, and if you have only trivial factors, then it's a prime. But then again, nobody tests like that, right? Everybody knows that you don't really have to test them all. We need to test only up to square root of n, and of course we'll prove that. Assuming that we proved, we can go through with a little bit more efficient way to find prime numbers, which is typically associated to Eratosthenes, and yes, this is the same Eratosthenes that's associated to the measurement of the Earth. The person who measured the circumference of the Earth and the radius of the Earth some 200 years BC. Is it 200 years BC? Definitely more than 2,000 years ago. That much I'm sure. But this is a method that's much older than Eratosthenes, as a matter of fact. It's not discovered by Eratosthenes. It's much older, much older. Mathematicians and historians nowadays are certain that ancient Babylonians and Sumerians knew about prime numbers and this prime sieve argument. It's just that Eratosthenes' record is one of the oldest, maybe the oldest, I'm not completely sure, and somehow the name stuck and people still call it this way. How do we actually work those out? Instead of testing for each candidate one at a time, consider a pool of numbers like this from 1 through 100 and then test them all at the same time. Write those like this, and then 1 is of course not a prime, and 2 is prime number, all right, and then cross out all the multiples of 2. So all the numbers that end with 2, 4, 6, 8, or 0. And then next, 3 is a prime number, all right, and then cross out all the multiples of 3. So cross out as increment of 3. So 6, 9, 12, 15, 18, those kind of things are all out. And then how about 4? It's already out. We don't have to worry about that. Go to 5 and cross out all the multiples of 5. All the numbers that end with 5 or 0. 6 is already out. Go to 7 and cross out all the multiples of 7. And then 8, 9, 10 are all out, and that's it. We don't have to do this anymore because we reached square root of 100. That's a magic number, square root of n. We'll prove it, of course. So in this process, we were able to cross out all the composite numbers between 0 and 100, between 1 and 100, and then what's left, or the numbers that sieved through, are the prime numbers. That's why it is called prime sieve. There are other prime sieves actually, not the one by this method associated to Eratosthenes, but they all have their own problems. Number one, they're all much harder, much more advanced, so I'm not going to talk about any of those. That's one biggest reason. Another aspect is they're not very good detecting all those primes there. They leave out some primes. They're much faster, but they leave out some primes. Many primes, actually. So no other prime sieve is perfect. Only this one is perfect, but the problem is it's very slow. Up to 100, we can do it like that, but if you have up to about 100-digit number, good luck. So 10 to the 100 power, up to Google, write everything and then cross those out. Good luck about that. It'll take seriously lifetime of universe to get these done. So those kind of things are called prime sieves, and then associated typically to Eratosthenes. but we have to prove it. Up to square root of n, that's a magic number. Let's prove that. Here's a theoretical foundation for all those methods. If n is a composite integer, then it has a prime factor less than or equal to square root of n. So up to that point, test, and then any further, you don't have to. Why is that? Well, because of the prime factorization lemma, n must have prime factors, and n is a composite integer, right? So it can be written like this: p times q times possibly more primes. Oh, one more thing. Prime factorization not only exists, but it's unique. So it should be uniquely like this. And possibly more primes may include more powers of p or q, and p and q may be the same, still okay. Now we claim either p is less than or equal to square root of n, or q is less than or equal to square root of n. Either one of them, maybe both, has to be less than or equal to square root of n. How do we prove it? Let's suppose the opposite. Suppose that both are greater than square root of n, and let's try to find a contradiction from that. And once you set that goal as a proof by contradiction, the proof writing becomes easy from this point on, because it's going to be nothing more than just a little bit of underestimation. So n is p times q times some possibly more primes, which I just highlighted in red. But what if I just drop it out? Bring those down to 1, then I've underestimated, so I'm going to get less than or equal. So we went down a little bit. And then p goes down to square root of 1, and then q also goes down to square root of n, and those are strictly decreasing because we assumed they're both strictly greater than square root of n. But then again, square root of n times square root of n is n, so what do we have? N is strictly greater than itself. That can't be right, so there goes our contradiction. So our assumption that both are greater than square root of n is wrong, so one of them has to be less than or equal to square root of n. So any composite integer has a prime factor less than or equal to square root of n, so we can test only up to square root of n. That's the theoretical foundation of this Aristotle's prime sieves method. As I wrote over here, there are other prime sieves that are more computationally effective, but each comes with its own drawbacks. And the drawbacks mean, number one, they are very difficult. Number two, they leave out many other primes. But then again, if you do not want to spend a lifetime of universe simply testing and getting nowhere, you'll have to do something different. So people are still studying other kind of prime sieves these days. Now, in prime sieves here, we did some trial division. And is there some effective way to see some trial division without going through all kind of actual division? Let's discuss that. According to our textbook, it shows up, I forgot the exact chapter, it shows up way later, but I think it's good time to discuss that right here because we are doing this computational aspect here, and then we are actually doing trial division. So to test some divisibility, there are several criteria that are useful if you remember. And the first set, everybody probably knows already. An integer is divisible by 2. That's equivalent to the last digit divisible by 2. So the last digit is 0, 2, 4, 6, or 8. Also, integers divisible by 5, the last digit is divisible by 5. So the integer ends with 0 or 5. And these kind of numbers called even numbers in particular. And then the next one, some people may know, some people may not. An integer is divisible by 4 is equivalent to last 2 digits are divisible by 4. For example, if you have something like 5, 6, 7, 8. Okay, all right, I just made it up. Whether this is divisible by 4 or not, I don't have to worry about all these. I only have to test 62. And 62 is not divisible by 4, right? 60 is divisible by 4, 4 times 15. So this one is actually not divisible by 4. It has remainder 2. You can test like that simply by looking at the last 2 digits. Are you familiar with this method? And then same thing goes to divisibility by 25. 62 is not divisible by 25. So, for example, if this had been, say, 75, then we have 75, and that's congruent to 0 mod 25. So it's divisible by 25. Yes, you can say things like that simply by looking at the last 2 digits. And then how about the last 3 digits? Divisibility by 8 and also divisibility by 25, 125. And then as for the last 4 digit, last 5 digit, we'll have more, but hey, what's the point? Let me draw a line here. Let's discuss why this one works out, and then in the next video we're going to talk about a little bit harder test. The reasoning is pretty simple actually, as you can see from this example. The key idea is because 10 is divisible by 2 and also by 5, because 10 is 2 times 5. I can decompose this thing by multiple of 10 plus the last digit, and multiple of 10, well, that's modulo 0. That's 0 modulo 2 or modulo 5. That's divisible by 2 and divisible by 5 because this is divisible by 10. So we are left with only the last digit. I just gave you an example here, but you can re-express it as a power series with all those symbols, and you can go ahead with the general proof if you want to, but that's left to the students. How about the last 2 digits? That's because 4 times 25 is 100. That's the big reason. I can decompose into last 2 digits, and then this part divisible by 100, and 100 is congruent to 0 modulo 4 and also modulo 25. This part doesn't contribute. So the remainder part comes from 24 only, and 24 is divisible by 4. So yes, this number is a multiple of 4, but it's not a multiple of 25 because 25 does not divide 24 in this particular case. How about this one? Well, you guessed it. 8 times 125 is 1000. So I can decompose last 3 digits away, and then what's left is 1000. And 1000 is divisible by 8 and also divisible by 125. So this part here is 0 modulo 8 or modulo 125. So what's left is just 3 digits. Those kind of divisibility test is going to be useful when testing for primes or whenever you're doing some trial division without calculator. Let's come back and discuss a little bit harder aspects of this divisibility test in a separate video.